Okay, let's have a look at question 3 of the physics paper. Okay, so this is dealing with vertical projectile motions. It says that a hot air balloon is moving upwards at constant unknown velocity. Okay, there's a reason why it's all in capital letters. So think about what it means to be moving at constant speed. Okay, then 3.1 says, is the hot air balloon in free fall? Choose yes or no and give a reason. Okay, so what is the definition of free fall? It's when gravity is the only thing acting on the object. Okay, so if we look at the hot air balloon, it's moving at a constant velocity, which means that our acceleration, okay, is equal to 0. So because acceleration is equal to 0, and it's moving at a constant velocity, or acceleration is constant, your acceleration will be 0, yes. Therefore, it is no, okay? So no, because gravity is not the only thing acting on it. Not the only force acting on it. Okay, why is that? Well, if it's moving up a constant velocity, it means something is propelling it upwards. Therefore, something's pushing up as gravity is pulling down. Okay, now, then says, when the balloon is 200 meters above the ground, a small stone A is dropped from the balloon. See the diagram above. Another small stone B is dropped 5 seconds later from the balloon while the balloon is still moving upwards at constant velocity. Okay, stone A strikes the ground at 62.68 meters per second. Ignore air resistance. Now, 3.2.1 says calculate the speed of the hot air balloon. Okay, so note that when you're in the hot air balloon, okay, let's say this is my stone. If I'm in the hot air balloon and I'm holding the stone, okay, I am moving at the same speed upwards as the hot air balloon. Therefore, the stone is moving at the same speed upwards. Okay, so the stone is moving up at v constant. And that's what we want to find. So we need to find the initial velocity of the stone given that the final velocity of stone A is 62.68 meters per second. So we're going to use the following equation. Vf squared equals to Vi squared plus 2a delta y. Okay, why are we using this one? Okay, we have the height. We know what acceleration is when we're dealing with vertical projectile motion, and we have the final velocity. We're looking for the initial velocity. Okay, so note that I'm taking down as negative and up as positive. This is important. Now when I substitute my values in, it becomes negative 62.68 squared equals V initial squared plus 2 times my acceleration is down as well because gravity is acting down, so it's minus 9.8 equals, or multiplied by my distance. Now note that down is negative, therefore my distance is a negative displacement, so that's minus 200 as well. Okay, if you took down as positive, then all of these just become positive values. Okay, now if we substitute, or if we just manipulate, we're going to take that over and then square root everything, and you'll get an answer of V initial equals to 2.96 meters per second negative 1. Okay, note that it is a positive answer, and I've stated that up must be positive, therefore I don't have to indicate the direction, okay, because the positive indicates my direction. Now, 3.2.2 says the time it takes for stone A to strike the ground. Okay, so how long is it in the air for? That's what we want to know. Okay, so once again we have V final. Okay, that's 62.68. We've just calculated V initial. That's 2.96. Okay, we have the distance. It's delta y equals to 200 meters. But why aren't we using this 200 meters for this calculation? It's because, okay, we're first of all looking for time, but once I let go of the stone, okay, yes, that's the height it's moving up. Oh, we could actually use it, to be dead honest, because we know the exact height when we drop the stone. But in this case, we're looking for delta t, so we're going to use the following, apologies for that, we're going to use the following equation because we want delta t. Okay, so we are going to use v final equals v initial plus a delta t. Okay, pretty straightforward. V final we know is downwards, so that's going to be minus 62.68. Okay, we know that our initial velocity was upwards, so that's 2.96, it's positive. Okay, plus my acceleration is down again, so 9.8, and we want delta t. Okay, now if you just manipulate your algebra over here, you are going to get delta t equals to 6.70 seconds that the stone is in the air for. Okay, now 3.2.3 is a little bit of a tricky one. It says the distance the distance between the hot air balloon and stone B the instant stone A strikes the ground. Okay, so the minute that this stone hits the ground here, okay, what is the distance between stone B and the hot air balloon? Okay, so how are we going to figure this out? Well, the first thing we know is that stone A is dropped, and then 5 seconds later stone B is dropped. Okay, so we know that there is a difference in time between these two of 5 seconds. Okay, therefore, if we calculate where how long the stone's been falling for, okay, when A hits the ground, we can then calculate we then have the time interval for which the hot air balloon had to move upwards. Okay, so we are going to take the change in time between how long it took A to hit the ground and for B to be in the air. Okay, so what do I mean by that? We are going to take this 6.70 seconds minus the 5-second delay, because remember, 5 seconds after dropping A, we then drop B. So therefore, B's only been in the air for 1.7 seconds. Okay, now that we have this, we can calculate the height that the balloon will be at, okay, or how far it's traveled in 1.7 seconds. But we also need to know how far down, okay, the rock has fallen. Okay, so we've got to do two calculations here. The first calculation is going to determine the height or how far from the hot air balloon the second rock B has fallen. So we're going to use the following. Delta y, okay, remember we're working in the y-axis, so please don't use delta x, it's delta y is going to equal to v initial, change in time, okay, plus a half my acceleration, delta t squared. Okay, I'm using this because we have the initial velocity of the stone B, okay, because it will be the same velocity as the hot air balloon. I have my time, okay, that it would be traveling for, and I have my acceleration, therefore we can calculate delta y. So delta y equals to 2.96 times 1.7 plus a half, negative 9.8, okay, remember it's acting down, times 2.96 squared. If you plug that into your calculator, you're going to get a distance of negative 9.13 meters. Okay, so that's how far the stone is from the hot air balloon after 1.7 seconds. Okay, so that there is 9 meters. Okay, that's if the balloon was stationary, but remember this thing's moving up, so I need to add that additional height. So let's say the balloon's now here, okay, after that 1.7 seconds, so I need to find this additional height as well. So once again we're going to use delta y, okay, is equal to v initial delta t plus a half a delta t squared. But remember what it said in the beginning, it's moving at constant velocity, therefore my acceleration equals 0, so this whole term here is going to fall away. So to find the distance it's traveled, it's just the velocity times the time it's been moving. Okay, so delta y equals to 2.96 times 1.7 seconds, plus that becomes 0 because acceleration is 0. So therefore delta y moving upwards for the balloon is then going to give you 5.03 meters. Now we can find the total height. So h total is then going to equal to, let's call this delta y1, delta y2, so delta y1 plus delta y2, okay, which then equals to the magnitude of each one, so that is 9.13 plus 5.03, which then gives you 14.16 meters. Okay, so once this has traveled up 1.7 seconds and the stones traveled down 1.7 seconds, the total distance here is 14.16 meters. Okay, then lastly it says draw a graph, okay, on the same set of axes, draw a position time graph of both the hot air balloon and the stone. Okay, so the nice thing about position time graphs is pretty much what happens with the object, so the motion it follows, that's what the graph looks like. So the important thing is we started with some initial speed for the hot air balloon and we continued moving up at a constant rate. Okay, so this is position. Okay, and then this will be time. Okay, and they're asking use ground as zero reference. Okay, we're looking at it from the moment the stone is dropped. So my starting position is 200 and not 0. Okay, this is where my graph's going to start. Now, because acceleration is constant or equals 0, that means the graph is just on the 0 line. It means my velocity is constant. Velocity time graph is constant, which means my position time graph must be a straight line. Okay, we know this from derivatives. The derivative of a straight line is constant, derivative of constant is 0. Okay, so from here the balloon's just going to move up at a constant rate as time goes on. Okay, but now what happens with the stone? If you throw a stone from the ground, it follows that projection. Okay, but now when we're moving with the hot air balloon, I'm holding the pen, we move up and then I let it go and then it starts falling down. So it still follows the following shape. It's going to do that. So it's moving up at the same speed as the hot air balloon, and at this point here gravity takes over and pulls it down and therefore it accelerates downwards. Okay, and that's how we do this question. Okay, if you guys are finding these physics videos helpful, then please leave a thumbs up on the video. Okay, it was a bit of a tricky question, especially dealing with finding the distance for B and then maybe the graph at the end, but make sure you understand the graphs and how they work. Okay, if you guys are enjoying the content as well, then please subscribe down below. Go check out the channel. There's plenty of videos on these topics as well. If you guys have any questions, leave them in the comment section down below. I'll get back to them as soon as I can. And remember, it's never too late to have an OIC moment.